Hi, grade 9s. So we're going to get started today on concept D2, which is related to technologies or states technologies can be transferred. Let's try again. Technologies can be used to transfer and control electrical energy, and what we're going to be focusing in on today is the idea of controlling current. So just remember that current is moving charge along a conductor, and it's measured in amps. So let's just dig a little bit deeper into what that all means to us. I'm going to skip over this slide, and if we get some time tomorrow, then we'll jump into looking at a couple of these videos. So controlling the flow of electrical current. Electrical current flows through a complete circuit. Remember we said that if the circuit is broken for some reason, maybe there's a switch on it or a wire has been cut, then the electrons stop flowing at that point. They can't jump across a gap. The amount of current that can flow through a circuit is limited by the conductive properties of the components in the circuit. What that means is how much current a circuit can carry is a factor of the properties of the components in the circuit. In other words, how well does the metal wire conduct things? What sort of resistors are in place? Those kinds of things. So in other words, the amperage, the speed of the charged particles, is dependent on how well the object conducts electricity. This means that it is not that electricity does not flow through materials such as rubber or wood, but that the flow is slowed so much that the material remains neutral. It just basically stops flowing at that point. So rubber and wood conduct, but just so little gets through and so slowly that it's nothing that we really worry about. So in order to get into this, we want to talk about insulators and conductors again. So in insulators, the electrons cannot move easily. Okay, so an insulator, remember, is something like rubber or wood or something along those lines. In conductors, though, electrons can move easily because they are not tightly bound to the nucleus of the atoms. So this is what an insulator might look like over here. The electrons, which are the negative, blue in this case, are bound tightly to the nuclei, which are the positives here, and so they resist movement. A conductor with no voltage applied shows that those electrons are not as tightly bound. They can drift away from the nucleus, right, which are the positive parts, but they don't flow in any one direction. However, when we apply a voltage to the conductor, then the electrons flow towards the positive terminal. So in other words, if the positive terminal is over here, those electrons are attracted towards that positive terminal. So the insulators are what happens when we get the nucleus and the electrons tightly bound. A conductor means that those electrons are a little more free flowing. They're not as attracted to the nuclei, meaning that they can be made to flow towards the positive terminal in a voltage source. There's also things out there called superconductors. And superconductor is a material that has no resistance to electron flow. Okay, many materials are superconductive, but can only be done at very low temperatures. Tomorrow we'll jump back to this link and we'll have a quick look at superconductors and what's up with them and how they work. But remember the name superconductors, because I think it's going to be something in the future that's going to become very important. So using conductors, resistors, and insulators. Why might it be important to know how well different materials conduct electricity? Stop for a second and think about that. So resistors are parts of a circuit that might provide high resistance to reduce the amount of current flowing through the circuit. Resistance, just so we're clear, is a measure of how difficult it is for electrons to flow through something. So high resistance means that it makes it more difficult for the electrons to flow through a particular conductor, whereas low resistance makes it quite easy. So a superconductor would be something with fairly low resistance, if not no resistance. And resistance is measured in something called ohms, OHMS, that is spelt correctly, and it's unit symbol is this omega symbol. That's the Greek letter omega. Kind of looks like somebody bending over. Anyway, so where do we use resistors and why are they important for us to have a look at? The more resistance a substance has, the more the substance gains energy from each electron that passes through it. The energy gained by the substance is radiated to its surroundings as either heat or light energy. So some examples of devices that use resistors would be things like a polygraph machine. Polygraph is a lie detector, if you sort of think to some cop shows. Microwaves use resistors, and touchscreens also use resistors. Solutions can also be resistors. The more charged particles in a solution, the better it conducts. So think of pure water versus salt water. Pure water doesn't conduct nearly as well as salt water does because salt water has ions in it. Let's talk about polygraph machines for a second. A polygraph machine, or a lie detector, is designed to measure skin resistance, blood pressure, and perspiration. To measure the changes, so for example, to measure the changes in sweat, which is a salty solution, we attach electrodes to the skin. And so somebody might not give off any physical signs of being, nervous or lying, but we can pick up those signs by maybe just a little bit more increased sweat on their skin. And again, we can have a look at this this video tomorrow as well. I think that's what we'll do, is we'll just run through a bunch of videos tomorrow and sort of see where they end up. So polygraph machines are designed to measure either skin resistance or blood pressure or something along those lines, and that resistance means the saltier that the skin becomes, the less resistance it has, so more electricity will flow through those electrodes on the skin, and we can detect when somebody might be lying. Switches create a break in the circuit that interrupts current flow, therefore controlling the flow of the current in a circuit. And we use switches all the time. I mean, a light switch and dimmer like this is one of the most common examples of a switch. Something called a variable resistor is another type of control of the flow of electrons or control of current. These resistors, variable resistors, are also known as rheostats, and they allow one to adjust the amount of current flowing through a circuit rather than simply turning it on and off. So there may be some cases where we want more flow or less flow, and that might have to do thinking about a light, for example. If we want a brighter light, we may want to have more flow, and so we're going to use a rheostat to control how much flow we have going to that light bulb on our circuit. Take some time after we're finished with this video and go and have a look at page 302 for some examples of rheostats and where you might find them in your daily lives. I'm going to skip over these check your understanding questions for now. We might jump back to them tomorrow. Just to point out that I'd like you to complete after you go to page 302 and find some examples of rheostats, I'd like you to go to page 303 and work on questions 1 through 4 and 6. And like I promised, we will jump into some of those videos tomorrow by way of to review a little bit what we were doing. So I hope this gives you a better understanding of resistors and how we can control the current flowing through a circuit. And hopefully the rest of this goes well for you, and we'll see you tomorrow.